In the previous set of videos, we saw some Laplace transforms of basic functions, such as the Laplace transform of 1 being 1 over s, and the Laplace transform of e to the at being 1 over s minus a. Much as with derivatives, once you have a derivative of a function, the inverse gives you an integral rule. And that's what we're looking at, well, the equivalent of that down here. We have inverse transforms. And we'll look at transforms of derivatives later. But for now, since the Laplace transform of 1 is 1 over s, the inverse transform of 1 over s is 1. And likewise, since the Laplace transform of e to the at is 1 over s minus a, the inverse transform of 1 over s minus a is e to the at. I know we haven't yet seen why these are useful, but that'll unfold over time, and for now we're just going to work with finding inverse Laplace transforms. We have here the inverse Laplace transform of 1 over s to the fourth. And looking at our list of inverse transforms here, we see that the inverse transform of something with s to the power, to a power in the denominator, will transform to t with an exponent. Since the exponent on s in the formula is n plus 1, when we see 1 over s to the fourth, we can identify that n is equal to 3. Therefore, we can rewrite this transform as the inverse transform of a denominator of s to the fourth. And folks, we need an n factorial in the numerator. 3 factorial is, of course, 6. And so what I'm going to do is multiply and divide by 6. And it should bring to mind like integrating using the substitution rule. We multiply and divide by 6 so that ultimately we're multiplying by 1. And because of the linearity of the inverse transform, I can multiply by 6 inside the brackets and multiply by 1/6 outside the brackets. The bottom line here is that since the inverse transform of n factorial over n s to the n plus 1 is t to the n, the answer here is 1/6 t cubed. Next up, we're looking at the inverse transform of 10s over s squared plus 16. I'm looking in our rules for inverse transforms for a denominator that has an s squared plus a number, but also that has a factor of s in the numerator. And we see here s over s squared plus k squared inverse transforms to the cosine of kt. Since here we have s squared plus 16, we can see that k is equal to 4. And so the inverse transform is 10 times the cosine of 4t. If you're wondering about the negative 4, remember cosine is an even function, and so if you made this a negative 4t, you'd get the same result. And then if we turn our attention to the sine function, we would need a k in the numerator, just like we needed an n to the fourth in the numerator of the previous example. If we decided that k was negative 4, then I'd have a negative 4 up here as k, and then in the sine function I'd have a negative 4, and since I would have to multiply by the negative here, I'd need to offset it. That would get washed out by the fact that the sine function is odd. Bottom line, you never need to deal with the negative here. Next up, we've got the inverse transform of s plus 1 over s squared plus 2. That denominator has the form of s squared plus k squared, and even though 2 isn't a perfect square, it's the square of something. And so we can see that k is equal to the square root of 2. That puts us in sine or cosine territory, but we don't have anything that tells us what to do with a numerator of s plus 1. Well, that's what I'm here for. I'm going to tell you that we're going to take that numerator and split it. We're going to make two fractions. S over s squared plus 2 plus 1 over s squared plus 2. It's the same k both times. With the s in the numerator, that's going to give us a cosine. With the 1 in the numerator, that's going to give us a sine, but remember, we were just talking about that k in the numerator. K is the square root of 2, so we're going to basically do what we just did 2 examples ago, and I'm going to multiply and divide by the square root of 2 there. Notice I'm not putting the 1 over square root of 2 outside of the whole thing this time because it shouldn't affect the cosine term, or the term that'll become the cosine if you want to be accurate. This gives us the inverse transform of the cosine of the square root of 2t plus 1 over square root of 2 times the sine of the square root of 2t. Next up, we have an entirely different situation. The inverse transform of s plus 1 over s squared minus 4s. Now, I don't need to show you the list to see, for you to see that there's nothing on that list that gives us s squared minus 4s in the denominator. Folks, when we can factor a denominator like this, we are more than likely going to be using partial fraction decomposition. So I'm going to write the expression, the inverse transform of s plus 1 over s times the quantity of s minus 4. And this is going to come up fairly commonly throughout this chapter. If you need to review partial fraction decomposition, absolutely do it. I'll give you information as we go as well. And the fraction s plus 1 over s times s minus 4 will decompose into fractions that have denominators of s and s minus 4. Both of those denominators are linear, therefore we need constant numerators, and so I'll write down a over s plus b over s minus 4. If you imagine clearing the fractions, then you get s plus 1 is equal to a times the quantity of s minus 4 plus b times s. We can zero out the b term by letting s equal 0, and we will get that a is equal to negative 1/4. We can likewise zero out the a term by making s equal to 4, and we will find that b is equal to 5/4. So our expression becomes the inverse Laplace transform of negative 1/4 over s plus 5/4 over s minus 4. I wouldn't submit this as a deliverable, like a final answer, 5/4 over s minus 4, but for partial fraction decomposition, I almost always do it that way. The inverse transform of a fraction that looks like a constant over s is 1, right? So negative 1/4 over s inverse transforms to negative 1/4. If we had 1 over s minus 4, that would inverse transform to e to the 4t. That 5/4 comes along for the ride, so our final answer is negative 1/4 plus 5/4 e to the 4t.